Hello, how are you today? In this video, you'll learn the basic concepts of binary search trees, how they work, and why we should use them. And after I explain the basics, I'm going to guide you through the process of searching and inserting data in a binary search tree in Golang. So yes, let's see what we have. Okay, so as you can see, this is a tree structure. We call the top node the root, and the nodes that are directly under a node are called children. So the node above would be the parent. And if you see at the bottom of the tree, there are nodes with no children. These are called leaves. Here you can see that there are two children coming from one parent in this diagram. In this case, we call this a binary tree. A tree that has nodes with no more than two children is called a binary tree. So each parent is going to have a left and right child. And when the smaller child is placed on the left and the larger placed on the right, we call this a binary search tree. But most cases, a binary tree actually wouldn't look as perfect as this. Some of the left or right children nodes will be empty. So it would be more looking kind of like this. So in a tree like this, we're going to talk about how we're going to insert a node. Nodes are always inserted as a leaf. Let's say we want to insert a node with 56 as a key in this tree. We're going to start at the top and compare 56 to the root. So 56 is smaller than 100, so go left. And it's larger than 52, so go to the right. And it's going to be smaller than 76, so go to the left. But that spot, that left spot is empty, so 56 would be placed there, and that is how a node can be added into a tree as a leaf. It's also similar to when you want to search a node in this tree. So let's say you want to find a node with 24. You also start at the root at the top and you compare 24 to 100. It's smaller, so go to the left. Smaller than 52, so go to the left. Larger than 19, so go to the right. And it's there, so we found it. So we can say that 24 is in this tree. Yes, it's very similar how you insert it and how you search nodes. The advantage of using a binary tree is speed. So when the tree is well balanced, when we search or insert data into a binary search tree, the big O is going to be OH, which is better than an ON. It's log n. Even though the tree is perfectly unbalanced, which is like the worst case scenario, it would still be linear, which would be equivalent to a linked list. So a binary search tree would be pretty useful when you're handling a large amount of data. So this time we're going to go and try to implement this in code. Okay, so we're going to do three main things. We're going to define a node. And we also need to make an insert method because we're going to have to insert nodes in the binary search tree. And another method, we're going to do search. Okay, so these are the three main things that we have to do. Let's first define a struct for node. And inside, for the fields of the node struct, we're just going to use int for the key. Here we just need it to compare it with the other nodes. We're going to compare the key. Each node will be a parent. So if it has any children, it needs to have two pointers, which are going to point to each left and right child. And okay, let's just go and try to make one. So I'm going to make a tree, use a struct literal to and key 100. And because node, the tree should be an address, I'll have to put that there. Tree has to be an address. When I call methods, I'm going to call it as a pointer. And let's see what we have. Oh, capital. Okay. All right. Okay, so you can see that the key is 100. We didn't give anything for left and right, so by default they're going to be nil. So right now it's just a node with no children right now. Okay, nice. So now let's go do the insert. We need to manipulate the receiver, so we need a pointer receiver. And we have to take in a key which is not already in the tree. So we have to take So our plan is to compare the key with the receiver and go to the child on the right if it's larger, and go to the child on the left if it's smaller. So the basic structure inside the brackets in this method should look like this. So in n, the key, if k is larger, then we're going to move right, and if n.key, so if k is smaller, then we should move left. So that's going to be the basic structure. And so when we move to the left child, if the child is empty, we'll just put a new node there. So we're going to write that up in code. So this would mean if that right child is empty, we're going to make a new node, and the key should be k. But if there is a node at the right child, like right now, we're assuming that there's nothing on the right child, so that's why we're inserting it here. But what if there is something? We're going to repeat this method, this insert method, again on that right child, that existing right child. In other words, we're going to recursively call this method onto the right child. So it's going to look like this, n.right. So we're calling this insert method not on the parent, but on the right child. And this goes same for the left. But instead of right, it's left. So just to clear things up, this method consists of two parts: when k is larger than the key and when it's smaller than the key. So when it's larger, we're going to move right. If that place is empty, we're going to make a new node and put it in there with the key k. But if that place is not empty, then we're going to call this method again on that non-empty, that existing child node. And the same goes for the left. Okay, let's go tree.insert 50. Okay, so right now what it looks like is there's 100 and we put in 50, so 50 is smaller than 100, so it has to go inside the left child, which is over here. So it's stored as an address, as a pointer. Let's put in 200. Oh, and in that case, this time it went into the right child. And again, let's do something. Let's put 300 in it. So we're going to put 100, 200, and 300. And in this case, when we print tree, because 300 went inside the right child node of 200, we can't see it in tree. So you can still see that the left position, left child of tree is still nil. Okay, so we just check that it works fine. I think it works fine. Okay, so now let's implement the search method. Okay. Actually don't need to use a pointer receiver, but just to be consistent, I'm just gonna use a pointer receiver. And as a parameter, we're going to take in a key, so we still need to do this. And it's going to return a Boolean value. So if if a key value k exists in the tree, it's going to return true. If not, it's going to return false. So here we're going to do something similar to what we just did in the insert method. So if the key of the node we're at is smaller, go left. If not, go right. So it's the same thing. If and if it's not smaller and not larger, then it means that it's a match, it's equal to. So in that case, we need to return true. So that's the big structure of this method. Okay, let's fill in these brackets. So after we go right, we're going to repeat this method. So we're going to repeat it on right and search. And we're going to keep on searching for k, and we're going to return this. Okay. So this method, search method, is going to continue to be called, and it's going to move down the tree and return true when it meets a match. So it's not k, when k is not larger or not smaller than the key, then it's going to return true. But what if we don't meet a match? What if there is not a match? In that case, we need to return a false. So if n is nil, so the node that we're calling the method on, if it's nil, then that means that it's the end of the tree and we didn't meet a match. To sum up a little bit, if the node is not empty here, this part, so if there is actually something there, this is going to be ignored. If k is larger, it's going to go to the right and call this again. If it's smaller, then it's going to go to the left and call this method again. And if it's exactly the same, then it's going to pass all this and it's going to return a true. So now let's go and see if this works. I'm going to add a bunch of nodes. And let's try to find 76. So I'm going to search 76. And we need to print it out. Okay, so let's see if this works. Okay, it's true. So we do have 76 here. Let's try to search something that's not there. 400. Okay, so we get a false. So I think it's working fine. We'll just try a couple of more. Yep. Okay, so just out of curiosity, let's see how many nodes that is actually involved in this search. Outside of the method, we have to make a variable. I'll just call it count. And let's put it here inside. We're going to count one up every time. So every time this is called, it's going to count one up. And so here I'm just going to, so let's call this, right, so it says 4. When we are trying to find 276, it's going through 4 nodes. Okay, I hope you got a good understanding of how binary search trees work. Yeah, that's it for today. I thank you so much for watching this video. Please subscribe and I will see you in the next video.